Welcome back, Pre-Calculus. This is the second part of section 10-1, 10-1, dealing with some of the topics of analytic geometry. This section, we're focusing on lines. And again, as I said, when we're looking in chapter 10, we're going to be getting into lines. We're going to get into conics. We're going to get into rotation of a conic. We're going to look at some new things that deal with polar coordinates or even rectangular coordinates. Again, you'll probably find this chapter rather interesting. I shared in the first part that we're going to have two tests in this section. I will let you know well in advance when the test is. All right, so let's finish up section 10-1, where we're dealing with analytic geometry, dealing with lines. And today we're going to look at Roman numeral 3 and Roman numeral 4. Roman numeral 3 now is going to deal with the distance between some point and a line. Now this point is not on this line, so we're going to have to find the distance between this point and the line. And again, it's found on pages 730 to 731 in your textbook. And again, the only way to do it is by showing examples. Okay, I got one bullet point here. So the distance d between some point x1 and y1, that's your given point, and the line, which they're going to have it in this form right here, guys. This is a little bit different than what we're used to. I know before we did ax plus by equals c, but we're going to set it up in this form. This right here is the formula we're going to use to find the distance between some point that doesn't fall on that line, and we're going to use this formula. This is going to be relatively just mostly calculator work on this one. The derivation of this, it's in your book. I'm not certain what page it's on, but again, I'm not going to really get involved in that because it looks like it deals with a little bit of Pythagorean theorem and looking at a triangle based upon the point and the line, a right triangle specifically. All right, so here's our example. Find the distance between the point 2, 3. Now I have graphed the point 2, 3, so x is 2, y is 3, and the given line. Again, I have taken the time and graphed this line. Again, we can do this problem by the x and y-intercept method. Well, the x-intercept is going to be 0, and the y-intercept is also going to be 0, so we can't use that part. So for you to do this one, to graph it, to see what it looks like, again, we just solve for y. So that would be y equals x, y will equal 4x plus 0. Y-intercept is 0. And we notice, I think I messed up here, divide both sides by 4. Yep, I just did the math in my head without thinking first, 1/4 x. So again, you see here that your y-intercept is 0, and we have a slope of 1/4. So it goes up 1, run 4. So here's our line, here's our given point, and we need to find this distance from this point to the line. And it's based upon a right angle. And all you got to do in this case is just use this formula. We could have done something else in this matter if you like. We could have treated this as a right triangle. We could have done that. Again, the distance really between this point right here is the Pythagorean theorem. But again, it may take a little bit of time doing this. So the mathematicians of our times went ahead and already did all the work for us. So this is the formula we're going to use. All right. Set it up. Again, you can leave your answer in radical form if you like, or just go ahead and use your calculator. And again, I'm not really certain. Bob may either have it as radical form, or Bob could have it as rational form. So I think you're going to probably keep it to this part right here. That's the distance between a point and a line. Okay, I think you guys can handle that. All right, let's go to the second part. Roman numeral 4 is an application of two distance formulas. All right, so I guess the only way to do this is by showing an example. So consider a triangle that has the vertices of 0, 0, 1, 5, and 3, 1. So this is a triangle, and we want to find the distance formula here from something. Okay, we don't know. It comes in two parts. Find the altitude from vertex B to side AC, and we want to find. Man, I'm going way too fast. Here's our triangle. Slow it down, Mr. Kosh. Here's our triangle, and we want to find the altitude from vertex B to side AC. So in other words, that's this part right here. This is the altitude of this triangle. Now this goes back to geometry days. We know it's a right angle right here, so that means this angle, this triangle, and this triangle right here are going to be right angles, and we want to find the altitude. But if you really stop and look at it, it's not that difficult. Here's side AC, because we can use this formula from the last section, because all we're doing is we're trying to find the distance from vertex B to this line right here. Here's your line. Here's your point 1,5. We're trying to find this distance here. Then we want to find the area of this whole entire triangle. You guys with me? All right, so right hand side is I found the length of AC. Must have some importance in a minute. So I found the length of AC by using the distance formula. So we know the length of AC is radical 10. So let's apply some rules. So letter A, find the distance between the point 1,5 and the line AC. So we have to find out what the line of AC is. Again, you have done plenty of those in Algebra 1 and Algebra 2. We have found that this right here is the equation of that line. I don't need to go over that. You've done plenty of these by using either the point slope form or the slope intercept form. You guys can handle that. So to find this H, which is also the altitude from point B down to the line here, we use that distance formula in the previous Roman numeral 3, and we got it to be 4.427. So now we have found our distance from B to that line. Now letter B is asking us to find the area of this triangle. Now again, this is not a right triangle, so we can't use 1/2 BH, because the area of a right triangle is 1/2 times the base times the height. We have to do it in parts. So the area of a triangle is 1/2 times the base, but now our base is the distance AC times our height, which in this case, our height is the altitude here. So we go ahead, 1/2 times the length of AC, which we found to be radical 10, times our height, which is really this altitude. We found that over here. Okay. I put mine in as a radical expression, and all you got to do is do your math, round it if you can. We get an area of 7 square units. That, ladies and gentlemen, is section 10-1, dealing with finding an angle of inclination of a line. Finding the inclination of a line using tangent, angle of inclination between a line. 2, angle between two lines. 3, the distance between a point and some line. And 4, doing a little bit of application by this whole purpose of this one is trying to find the area of this triangle. But before we find the area, we've got to be able to find other information to be able to do it. So I think you guys will have a good time with this section. Take your time, think each question through. Don't be afraid to put it on, graphing it. It's not going to hurt you. Okay, application of your formulas. I think you'll have no problem. Again, one thing that I need to go and really draw your attention to, remember now, theta in our angle of inclination, or the angle between two lines, is got to be in degrees. That's the key. Remember that. And remember, those angles are going to be between 0 and 180 degrees. So if you got a different number that doesn't fall between 0 and 180, you might have done something wrong. So go back and think it through. All right, love you guys. I shall catch you later. We'll look at section 10 too in a couple of days. Catch you later.